My name is Uri Yanover, and I'm a software systems architecture lead at Immunite. I'd like to tell you 3 war stories about big data. As is often the case with war stories, it's not how we got there that matters, but rather how we got out of there. And I really hope to present you several interesting ideas about both algorithmic technique and about programming technique that allow you to analyze new problems, real-world problems, and treat them as they come up. The first war story dates back to the early days of Immunite. I'll tell you a bit more about that, but first I would like to talk to you about a basic concept in computing called sparseness. An intuitive definition of sparseness is exploiting the fact that data is distributed in a certain way in order to take up less space. Now, this always comes at a cost, and the cost is almost inevitably performance. So essentially, you are trading off less space for more CPU time. Let's consider a specific example. In this case, it's an array of 8 numbers, 4, 6 zeros, and 5. A very common move in sparse representations is what I call the index value representation, which is you say something like the whole is 8 bytes long. Specifically, the meaningful data is 4 at index 0 and 5 at index 7. And implicitly, the rest of the bytes are 0. So one can do some very easy math and see that under the assumption that your indices are also bytes, that kind of representation is useful when approximately half of your data or more are zeros. Conversely, if you are facing a dense data situation, which less than half of the data is 0, you will actually be losing space on this representation. And in any case, you will be paying a computational cost both to construct this representation and to access it. And a very common use case is accessing just a random index inside that data. So with an array, you can just go to that index. It's one CPU instruction. In this representation, you actually need to consider all of the index value pairs and pick up the value with the right index, or somehow treat the case in which the index that you want is not present. So, and the easy way to do that is just go over all of the indices. What a lot of people do and makes sense in a lot of cases is do a binary search, assuming, of course, that the indices are sorted. A close cousin of that technique is the run-length encoding technique. So for this vector, the run-length encoding is saying we have 1 time 4, 6 times 0, and 1 time 5. The generalization of this kind of techniques is compression. So on a practical level, compression means you take in a vector, you encode it to bytes. You could use the Python struct library or the NumPy convert vector to a disk file. There are several routines that do that very efficiently. And then when you get an array of bytes, you compress that array using gzip. This technique works great, and it doesn't make any assumptions about data. It kind of does a great job in reducing data size as much as possible. It's almost optimal in that sense. For example, if all of your numbers have leading zeros, it will catch that. If the most frequent element is not 4, but rather it's not 0, but rather 42, it will capture that too. So it will capture if you have like a long run of 0, 1, 0, 0, 1, or whatever. The major cost you're paying is the fact that compression is extremely expensive to construct. And whenever you should access any of that data, you don't even have binary search. You need to unpack a whole chunk of data. And to be meaningful, it has to be at least tens of kilobytes in size, and you need to go over all of that data. And just before we go into the specific mistake that I made, I would like to describe the context of why we even need to consider that. So I'm working for a company called Immuni, and Immuni wants to reprogram the human immune system, which could be transformative in the way that humanity treats things like cancer and type 1 diabetes and a bunch of other diseases, from heart disease to aging. So, okay, how does it connect to data? Well, our way to get an insight on this disease is by considering something that's called functional genomics, which is studying the way that genes express in our body specifically, as opposed to the general repertoire of genes that is kind of hard to study on its own. So what we practically do is take single cells and see which genes are activated at the time of our sampling. So what you practically get when you do that is typically a collection of several thousand instances of several hundred distinct genes. And if you try to represent your data using a matrix in which the rows are cells and the columns are gene identities, you'll find that the vastly predominant element of that matrix is 0, because most genes are not expressed in most cells of our bodies. So by definition, when you consider functional genomic data, it is sparse. And now, specifically to Immuni. So back in the early days, I was building a system that would take the outputs of our computational data pipeline and make it available to an application that's presenting data to doctors and researchers. And I thought that it would be nice to bundle data in my own kind of sparse data format. Really, that it didn't, for some reason, I didn't think about anything better than to build one of my own. And the idea was to take tuples of the form row number, column number, value, which is a form of the index value representation I told you about several minutes ago, and to put that into a Python zip file, which is an instance of the compression technique I told you a couple of minutes ago. Then we'll just have a zip file with all these things, and we could also add their metadata. So, for example, that the data is stored in a certain schema, and that it's described a certain kind of a source sample, and so on. And I even had a very awesome name for that. It was schwung, which means the groove or the flow, as in a programmer being in the flow. That probably should have been a flag from it. Well, so the thing is that there is actually a format called HDF5 that does everything we wanted from schwung and then a tiny bit more. It also supports memory mapped arrays and concurrent writing, which is super important because in some cases you could be parallelizing your workload to several threads, and then you would like to have a single output file. The memory mapped arrays is important because if the data is too big to fit in your memory, you still may want to access it just by picking one piece at a time. So, by the way, HDF5 is not unique. It's vastly popular in the scientific community, but also there is a new format offering schema computation, which is called ASDF. So, before I close the schwung chapter, I wanted to present a certain generic perspective on why it was a bad kind of decision. And it's really about two questions that I should have asked and did not ask in that specific case. Question number one is, how many distinct pieces of software are expected to use the format? Question number two is, does that software exist at the time of us developing the format? So let's consider several cases. When you're just choosing a data structure for in-memory operations, the answer to the distinct pieces of software bit is 1. So you are reading and writing the data in the same piece of software. And obviously it exists when you are creating the format. I mean, it's a part of creating the software. So there is no way you will miss a major functional requirement when you're just kind of, by the time you're done with everything. Okay, when you're developing an on-the-wire format, for instance, the format you send between the front end and the back end, the number of pieces of software that use this format is typically 2. And typically, you also develop them simultaneously. So you won't lose a major constraint for the front end if you're doing it right. However, a storage format is an outlier. So first of all, it's by definition used by 2 pieces of software, and typically it's used by many more than 2 pieces of software. And the reason that we don't even know is because you're storing that data and it's going to be useful only later. And when you do that, you are essentially blind to the kinds of use cases and the kinds of constraints you're going to have by the time people need to use your software. So for example, the fact that there is a lot of utility to be had from memory mapped matrices was simply not something we could think of when we were developing the Shmoon file format. And that's a good reason to avoid developing one if there is a decent one lying around. The second war story I would like to present is about connecting concepts. What do I mean by that? So a while ago, I was working in this company that was trying to model some aspect of the human language by presenting a kind of a knowledge graph in which there were concepts grouped together in the form of taxonomy. And having that is a standard technique in natural language processing to enable answering questions like, is a pangolin bipedal? Well, the problem with taxonomies is that you really need to fine-tune them very thoroughly to the specific use case you want to address, because really, in some contexts, pangolin is bipedal, whereas in other contexts, it's quadrupedal. And in some cases, you care about the fact that a humanoid robot is a concept, and in other, you don't care about that. So what this company was practically doing is to employ a huge team of domain experts that were curating and editing that taxonomy. And as part of that, they were constantly kind of trying to see if they have broken something old about that, which is totally easy and possible and obviously undesirable for business. And as part of their iteration, they needed to run a bunch of tests, and those tests relied on there being a comprehensive list of all concepts that are connected. So for example, in this case, an animal is a supertype of chicken. So animal and chicken are connected. Now, important algorithmic note, this connectivity is directional. So we care that chicken is a type of an animal, we don't care that an animal is a supertype of chicken. Okay, so when we consider the structure that we have on the screen, we easily see that it's a directed acyclic graph. And the problem that we were facing was to quickly compute all pairs connectivity in such a graph. Specifically, for the case that we were considering, the easiest path to make the computation quickly turned out to be to formulate it as a metrics problem. And it goes more or less like that. And if you want to ask me in the sessions part, in the questions part, like what's the exact intuition behind that? So if you consider the outgoing edges matrix for all of the nodes of that graph, all you need to do to find the connectivity is to find a certain polynomial of matrices. So add some matrices and multiply some matrices, which are all powers of the original outgoing edges matrix. And at least in terms of formulating the algorithm, that was the simplest way to go forward. Okay, so on the face of it, we have the matrix. It's like super easy, it's sparse. And NumPy supports sparse matrices. So we're golden, right? So we just plug it into NumPy. We do some power, some sums, and we're good, aren't we? Nah, we're not. Let's see exactly what NumPy calls sparse matrix. So NumPy has two mainline formats for sparse data, which is compressed sparse rows, CSR, and compressed sparse columns, CSC. And the idea behind both is similar, they're just the transpose of one another. So let's consider this simple example. We have a matrix with 8 values. It's a 2x4 matrix. And the first values in each row are zeros for our purposes, and the rest are non-zeros. So the zeros are sparsed out. How does it work? So first, we put all the non-zero values into a single array, which we call V. And we put them in the scan each row and row by row order. So in this case, the first row non-zero elements are B, C, D. The second row non-zero elements are F, G, H. And then we just put them in order in the first matrix V, in the first array V. And then we try to reconstruct where did we take each of these values. So we need to say that B came from column number 1, C came from column number 2, D came from column number 3, and F came also from column number 1 of the next row. Okay, so we store all the data in the array we call index. And finally, we need to reconstruct where each row begins. And to do that, we have a separate array called row index, which remembers the beginnings of each row. So, for example, the first row always begins at index 0. The second row, in our case, begins at index 3 in V and call index. So we put 3 there. And there is no third row, but in order to make some edge conditions work, we also need to store the last element in the index, which is not actually an element in itself. So we store 6 because this array only has 6 elements. It's actually pointing at the end of the V and call index arrays. And now let's consider how we multiply matrices. So what you see on the screen is a diagram from Wikipedia about how multiplication works. I won't bore you with the details, but it goes more or less like that. We go in parallel on the row of the first matrix and the column of the first matrix. And we multiply the respective elements at each index. And then we sum up this multiplication product. Okay, so let's see how it maps to the format that we have. Traversing a row in the CSR format is relatively simple. So for instance, we want the not 0 of the first row. So we take the third array that we have, and it says there are 3 at index 1. So it means that we need to consider the elements that go from index 3 to the next index, which is 6, in the first and second arrays. So we know that the row number 1 in that matrix is the elements F at column 1, G at column 2, and H at column 3. That's nice. But wait, what do we do about the columns? So here it becomes more complicated because we need to go over all rows. So that's already not super efficient because it's not necessary that all rows actually have any elements at all. And for each row, we need to do a binary search to look for the right index for the column. And that operation is quite necessarily not very effective. So we end up doing a binary search for all of the rows in that matrix, including we need specifically to check also for absent rows too. And that part introduces a slowdown, and actually a pretty bad slowdown. How can we get out of that mess? The answer is simple. Our problem in the previous approach was that lookup of an element by column was inefficient. So we could just speed that up. So one thing we could do is just use a representation in which, instead of having an array as representation of each row, we could just have a mapping or a dictionary as the representation of each row. And in that case, as you can see in the line that's exactly in the middle of the code here, instead of doing a binary search, we do an array get, which in Python is an O1 operation. Now, practically at hardware level, it's still slower than an array access, but practically it may actually be quite good enough for our purposes. Of course, we could also go for a more complicated indexing scheme involving some kind of an additional data structure. It turned out that it wasn't necessary for our purposes. So how can you actually measure this kind of stuff? So the answer is that in Python, there is a bunch of technique on how to measure both elementary operations and kind of end-to-end workflows. So you have a bunch of profiling tools. There is timeit, which is very useful for one-liners in the IPython command line. And there is also cprofile, which allows you to measure complete cases end-to-end. If you care about memory, you can use sys.getSizeOf, which is a way to gauge elementary data structures. And you have more advanced libraries that reverse the object graph and try to measure more complicated memory use cases. In any case, one thing that you will see easily is that dictionaries are extremely memory inefficient. So if you really need to store dense data, then our tip is not to use the standard Python dictionary for that. You probably can do better by some kind of an array. The third war story I would like to tell you about is about oversized JSONs. This also happened about 5 years ago when I was working at a different place. So essentially, this was a flattening problem while operating in an environment that doesn't really support the flatten operation natively. As an input, we were getting single records of the form that you have some data that's on top level of the record and some data that's split between about 1 million transactions. And what we really wanted to do is to take the top level data and to flatten it into the transactions, and then get a stream of records that are a combination of the two. So this is super standard. So what's the problem? The problem is that the input was in the format of JSON lines, and each specific line was taking as much as 1 gigabyte. And the environment we were running in was allocating about 2 gigabytes per executor, which practically meant that Python's standard JSON.loads was simply running out of memory. When it wasn't, it was still taking tens of seconds to even load the line. So iteration times in real data were horrible. So this does call for a bespoke solution. So here are some things I found out when I was considering that data. First, my kind of basic technique for these kinds of things is to try to use some regexes to pry the data out of the JSON. The problem here is that the data wasn't stored adjacently, which practically meant that the reg extension would also get stuck because the string size of the inputs was huge. Okay, so we can't go that way. What can we do? So the JSONs were all machine generated. So really, we didn't have a data validation problem. The pieces of that JSON, so the individual strings inside were small, hundreds of bytes. So we could load them part by part. We did need only a specific family of paths inside the JSON. And those paths were known in advance. So there wasn't like this kind of a lookup that we must remember the keys for. And probably the most relieving thing was that the general fields, the ones that needed to appear in each line of the flattened output, appeared before the specific ones. So we could just remember the generic ones, iterate over the specific ones, and then output a record for each specific entry. So we didn't need to cross-reference a lot of information, which would have been a harder problem. The approach we took was an online streaming single pass architecture, and what I would like to do now is to describe how we built that. So I wrote a lexical analyzer for JSON. In hindsight, it was a mistake, but we'll talk about that in a short while. So that lexical analyzer was spitting out navigation tokens. For example, we are in a new dictionary, or we are now considering the key part of the dictionary, and now we are past the value marker, which JSON is a column. And now we are going to the next key value pair, which is a comma. And that information was being stored in a state object. And it was used to operate business logic, which was, in our case, just printing out the flattened data that we were obtaining. First, let's consider the layer of just getting navigation data in. So here you see three functions. One is what happens when you see an opening curly brace, which is the beginning of the JSON object. And so in that case, you maintain a stack of paths. Essentially, what keys you needed to take to get to that point. So you allocate a new frame, that stack. And since you are not in any key right now, just say that this frame right now is invalid. So you don't really have any way to navigate to this point. Now assume that we are getting some key, for example, a string key. Then we can just alter the last frame of the path to be that key, and we are in a valid state now. Okay, assume that we process the key, we process the value, it's not shown on the screen, and now we are going on to the next key value pair. Then we need to first kind of commit to the key value pair restored. Perhaps we want to do some kind of operation involving that key value pair. For instance, output the data that we have stored in the state. And also we validate the path, because up until we see a new key, we just don't know which key we are under. Business logic is invariably like, we got to some well-defined path, we got some well-defined value, let's do something about that. So for instance, one kind of path is, or one kind of event about that is that we can now, we saw some kind of value on that's matching, that's kind of matched to the key that we want. So for example, we could be seeing the key endpoint. So we know now that the value that we're seeing is the current endpoint. So we store that. Or it could be that the path is transactions anything and timestamp. So we know that we need to store the current timestamp in the state. So that's one part of it. Another part of it is, okay, so now we are done filling the state. We now want to actually do something about that. And that typically happens when we exit a transaction record. So in that case, we just see that what we're exiting is a transaction record, not any kind sub-record there, and we actually take all the data we have stored and output that state as a flattened output entry. Okay, let's sum up this war story, and then let's sum up the entire talk. Well, first of all, the solution worked well. It was munching through all data. Indeed, it turned out that it wasn't really such big data after all. So there were just, say, hundreds of thousands of records there. So actually, I was surprised how quickly it went after I implemented an efficient solution. One major mistake I made was using my own JSON parser. So there is a little backstory here, and I'll tell you about that, but still is a mistake. So what happened was that I started developing that on JSON because JSON was a Python that could be run inside Apache Pig, which is the Hadoop infrastructure I was working with at the time. And I didn't have a lot of choice about that. So it turned out that JSON just wasn't up to the task. So I ended up using an alternate mode of Pig, which is called direct streaming, which is essentially just having an arbitrary executable go over all the data. And I could do that in CPython. What I didn't do at that point is to see if my half-baked solution could be simplified using a standard library. And only after I finished, I realized that there is a good library for CPython that I could use, which is iJSON. And I did get some weird stares when I was describing that, yeah, I hacked my own JSON parser. Not that it's so complicated, but yeah, I shouldn't have done that, totally. So my second takeaway for you is that you should really try to use regexes whenever you can. You can parse a huge number of use cases around JSONs, including escapes, including kind of somewhat weird end cases. You could do that with regexes, and you could do that quickly, and it will just get the job done for you. So I've done this literally at least 3 times on major projects in my career, and each time it was a major shortcut. Finally, I'd like to stop a bit and think what could have happened if the flattening that we were doing was requiring more information or information from more sources that we can store in memory at any given time. And one reason for that would have been that the order in which fields appear in the JSON would have been different. So here we had general fields appearing before the specific ones, but we could have easily had the other way around. So the specific fields, like in this case, the transaction timestamp, would appear before we even know which endpoint that transaction was in. And then we wouldn't know how to emit a transaction record without them. So the right approach here is to give up, in the sense that there is no way to make streaming work well with that. And what you really need to do is to split it into parts. So we might have had just still a single run, but one that would output separately the transaction records and the endpoint record. And then we would have needed a separate job that's not a streaming job that would actually combine. And the reason that it's not a streaming job is because the general case of lookups and cross-referencing data is not something you can do in a streaming architecture, but a lot of times you can still do it very efficiently. So for instance, in Spark, it's called shuffle, and you have a very good implementation of that. So as long as you split your data into mergeable chunks, you can still do each of the chunks separately as a stream and then combine them using shuffle. Okay. Now let's talk a bit about the ideas and try to summarize what tools I think are worth taking when you go forward out of this talk. So there is something super liberating when you don't have to keep all the data in RAM. It means that your designs are minimal, they're lean, they are well thought out, and it also means that your code is blazing fast. And that's like super awesome. Development velocity matters. One other takeaway that I think is worth taking, sometimes logarithmic cost is a major pain. So yeah, it's true that logarithm n is like, bounded for like any normal data size by about 20, but still, the fact that you have a logarithm cost that amounts to 20 times the slow up means that instead of code that runs in a second for a small test case, it would run in 20 seconds. And that often is not good enough. So the final point is about tools. So the truth is, there are some super great advanced tools that you could be using, like the CSR and CSC matrices in NumPy. They are fantastic. They are well optimized. They are well thought out, but you do need to understand the trade-offs that they represent. So the same goes for Python. Python's arrays and lists and so on are actually wonderful tools. Sometimes they are all you need to get a really good algorithm going. You don't really need to use any kinds of fancy network app stuff or fancy NumPy stuff. So yeah, they could be just good enough. Just go ahead and think a bit about like what assumptions you make and try to use your tools in the way that's appropriate to the problem that you're facing. And that's all I have for today. I hope that the lessons I presented here would be valuable. And again, sometimes it's the best thing of all is just to avoid bad fighting, but also it matters what you do to get out of one if you have enough bad luck to get into one. Thanks and bye.